Hello, today we will present the cam and follower mechanism. The team is confirmed by Francisco, Gerardo, Patricia, me, Carlos, and Esteban. Okay, first of all, what is the cam and follower mechanism? The cam and follower mechanism is a simple mechanical system in which we can convert a specific kind of motion into another one. We can have a variety of many motions. In this case, we had a rotational movement, and we want to create a linear movement or motion. What are the components? Mainly, they are three. The first one is the cam, the other one is the frame, and the other one is the follower. The cam, it's the one that it will be rotating. It has a specific form, and the follower, as the word says, it will follow that shape of the cam. What is the function of the frame? Well, it's really easy. It maintains the verticality of the follower. If the frame doesn't exist, the follower will be moving from side to side, and in some point it will fall. We have different types of cams. In this case, we use the flat follower, as we can see in this image. Why we chose it? Well, in engineering, or more specific in mechanical engineering, we can have a lot of functionalities. And something that we really liked about it is that we can have a really controlled motion, but also we can have a lot of precision. And we can be like playing with the shape of the cam to create different kinds of movements. All of those are linear, but we can have like one movement that it goes really fast, or it can go slow. We can be like having different options, and all of this we really liked about this kind of mechanism.
The objective for this product was to design and construct a functional cam and follower mechanism employing Lego components and motors in order to investigate the influence of varying the gear size on the rotational speed of the cam and the linear velocity of the follower. For our hypothesis, if the gear connected to the motor has more teeth than the gear linked to the cam, then the rotational speed and the linear speed on the follower will increase. But if the gear connected to the motor has fewer teeth than the gear linked to the cam, well, the rotational speed of the cam will decrease, resulting in a slower linear speed of the follower. These are our variables, in which the independent variable will be the gear size ratio, determined by the number of teeth on the driving and driven gears, as we can see in the image. The dependent variable will be the rotational speed of the cam and the linear speed of the follower. And for our control variables, it will be the voltage supply, cam profile, follower design, and stationary frame.
But on which theoretical background do we base this hypothesis? Well, for this, we use the gear ratio equation, which relates the angular velocities, or rotational speeds in this case, and the number of teeth of the driving and guiding gears. As we can see, the velocity ratio between these two gears, it's equal to the angular speed of the driving gear, the gear connected to the motor, over the angular speed of the gear connected to the pinion, or the guided gear. This, at the time, it's equivalent to the number of teeth on the guided gear over the number of teeth on the pinion or driving gear. We can explain this better with the image when we can see the number of teeth of 2 gears, and the relationship here is of 3:1. This is just an example, and we are going to explain now which type of gears we used. But first, we have to explain the experimental phases of this project. As we can see, the first phase was the design and planning of the project, where we decided we would use a Lego motor and mechanism. The second phase was the gear selection of the specific gears that we would make the ratio and the relationship. The third phase was to assemble all the Lego pieces necessary for the experiment. The next phase was the experiment setup, to put a camera that was fixed, so it did not move or tilt, so the measurements would be inexact. The fifth phase was to take the video, and then pass it to tracker on the sixth phase to collect data and analyze it posteriorly. The eighth and last phase was to make the conclusions and relationships between the results of the equations and the results given by tracker, and obviously to relate and to give the relationship of the ratio of change of speeds between the number of feet and the angular velocities.
So the equipment we used was a Lego technique set consisting of different gears and axles, also lift arms and pins, a Lego motor, a battery box, a tracker software, measuring tools such as a ruler, and an Excel for data recording. Also, this is optional, but we made a Lego base for stability. So in experimental procedure, we used first the motor, then we put 2 pins and 1 axle to the center, then we put a lift arm. We put an axle with a stud to hold 1 gear, and then we put the other gear. Then we start making the structure that is going to hold the follower. This is made by 1 pin, 1 axle, and 1 axle with a pin connector. In this axle with a pin, we put the axle with a stud that is going to act like a follower. And then we put 1 lift arm just to secure this structure. At the final, we put the radial cam, 2 radial cams, and then we connected the motor to our Lego base. We decided to put the battery box in the base so we can have a practical project, and also it was easier to transport it. And this was the final result. We changed the gears to 2 different positions, and you can see how the velocity is changing.
All right, so now we can say we have the video taken, we have the footage. How do we retrieve the data from it? This is where Tracker comes in. Tracker is a software which bases itself on locating a specific point on a specific part of an object throughout different frames of a video. And through it, we can obtain and modify the different columns to obtain, for example, in the case of the follower on the left, we can get the position in Y, the velocity in Y, and the acceleration in Y. And you can see that the results are pretty consistent. We can see a cyclical, or we can see that it has a period and the pattern repeats itself, which is characteristic of a cam and follower mechanism. On the other hand, Tracker also has a built-in protractor. So what it does is it allows us to measure the angular velocity of the cam itself, in order to, basically by seeing how much radians it moves per frame. This frame rate can be adjusted, and Tracker reads it in itself from the format of the video initially. In both cases here, we have a smaller gear ratios. However, in the bigger gear ratios, we will see that we have a larger standard deviation in the data, specifically when it comes to all of the rotational velocity, because the cam becomes extremely blurry when it's moving very fast. And so the Tracker software can't really place that very specific point in time and in the object. So we will now move forward. And we now have the data from Tracker. We now basically translate it into Excel. Why do we want to translate it into Excel? In the chart on the right, you can see that it has a lot of, basically standard deviation. There's a lot of margin of error, and this is due to several reasons. This is a video, the 24:8 gear ratio was taken at 204 FPS, which means that it basically has a lot more, it travels a lot more radians per each frame, right? And this is reflected on the numbers on the speed, right? Which is like up to 180 even. And on the other hand, on the left-hand side, we have the 1-to-1 gear ratio, which we can see is a lot more stable. The numbers are, not as amplified, right? And the blue curve are the measurements in Tracker. And then we also found out that there is a direct correlation between the average, the average of the angular velocity in Tracker to the predicted one, right? Which we calculate through the 1-to-1 gear ratio. And the orange curve is once we apply that that relation, we get the new values, and that comes like pretty much exactly as it predicted, with around a standard deviation of from 0.2 to 0 to like 20 in the case of the right one, right? Now, we also calculated the relation coefficient between the velocity of the follower, right, on the y-axis, and the and the rotational speed of the cam. And we basically did this by getting the maximum speeds of each like little cycle or period, right, throughout the whole interval of the follower. And we got those maximum velocities, made an average, and then we divided it through the pondered values for the rotational speed. And that's how we get the constants. As you can see, with the 8 to 24 and the 12 to 36 ratios, which are exactly the same, they do result in extremely similar coefficients, which means we're on good track. And basically the standard deviation between all the coefficients is around 0.001, which is very accurate.
This experiment, as any other experiment, wasn't exempt of error analysis. This is to make a little margin of error between the measurements. As we can see the height of the follower, we have an error analysis of plus minus 0.1 millimeters, which is the smallest measurement in a ruler, the tool we use to measure the gears. The standard deviation of the coefficient of relating follower velocity to the cam rotational speed is of plus minus 0.01 meters per second. The G ratio of angular velocity in 824 gear systems is of 1.189 radians per second. In a 1236 system, it's of 0.665 radians per second. On a 2036 system, it's of 1.223 radians per second. On a 24/8 gear system, it's of a 22.30 radians per second. This is a bit with a higher frame rate where it's going very fast. And the G ratio of the angular velocity in a 101 gear system is of 2.054 radians per second.
Finally, the objective of our experiment was to determine if the rotational velocity of the cam, as it got higher, was the maximum velocity of the follower higher. And as we can see, with the smaller gear ratios, the average maximum velocity of the follower is indeed smaller. And we can see that the ones with the same gear ratio, 12 to 36 and 8 to 24, they remain pretty much the same, of course, with a certain standard deviation, because tracker can't always locate the points exactly, right? On the other hand, we can see that as you start going up the gear ratios, the values for the maximum velocity of the follower increases. So we have concluded our hypothesis and proved that it's correct.